And we are recording, so I will hand over the floor to Group 6.
All right, welcome and thank you for joining us today. We are Gamma, which consists of Adam, Gabriel, Megan, Audrey, Max, and Alexi. This design incorporates a piston cylinder capable of holding between 10 and 200 microliters of fluid. The snap fit housing encloses the motor, piston, and tip ejector, while the tool key holder is mounted on the outside of the housing, providing a flush and seamless design. The overall size of this pipette is 60 millimeters wide by 69 millimeters deep by 205 millimeters tall. This comes in under the required size, making this design compact. The main feature of our design is how compact it is due to its concentric design. The images shown are side view when the housing is removed. The motor attachment is shown on the left image, which houses the shaft attachment and lead nut. The image on the right shows the inner workings of that system. The lead nut is attached to the shaft attachment, creating a larger piece that moves up and down the motor screw, creating the piston movement. A solid rod is attached to the shaft attachment with an O-ring to create the suction in the piston. The motor attachment has a hollow cylinder attached to the bottom, creating the outer housing for the piston. The shaft attachment has two prongs that slide through the motor attachment in order to push the spring-loaded tip ejector, as seen toward the bottom of the image. A limit switch is located near the motor to prevent the shaft attachment from colliding into the motor. Here is a video from testing demonstrating the piston holding and dispensing fluid.
Here, I will give an overview of the evolution of our pipette system. The components in each picture from left to right are the motor attachment, the shaft attachment, and the tip ejector. From the initial design to designs 2 and 3, the overall frame of the motor and shaft attachment was altered for a more modern look. The original design mimics current pipette designs, while the updated version brought a more sleek rectangular finish. The tip ejector was also redesigned to use less material and parts. However, the workings remain the same, as in there would be a circular extended part that pushes out the disposable tip. From design 3 to 4, the major change was of the shaft attachment. The rectangular shape was filled in and the prongs to push the tip ejector were widened to ensure the durability and sturdiness of this subsystem. From designs 4 to 5, the major change of the motor was of the motor attachment and placement of the limit switch. The motor attachment length was increased, which accounted for the distance the lead screw needed to move to collect the appropriate amount of liquid. The limit switch was moved to the inside of the motor attachment to decrease the number of moving parts. From designs 5 to 6, the major change was removing the cylinder and plunger to machine these parts instead of 3D printing them. This was to secure the seal these two mating parts would need to make to collect and hold liquid. From design 6 to design 7 and 8, there were small changes in each subsystem to assemble the entire pipette properly. Here we see the evolution of the housing subsystem. We use the original given design from the lab and altered a few components, including adding holes to the side of the housing to hold the motor attachment, moving the location of the hole on the bottom plate to be concentric with the plunger and cylinder, which also gave space for the wirings and limit switch, and on the same bottom plate, extracting a piece on the side to better accommodate the magnet that would need to slide in and out to retrieve and return the entire pipette system. From design 2 to 3, a complete design change was made to modernize and sleek out the entire system. The housing became part of the motor attachment to expose the skeleton of the pipette system. In the end, we chose a snap fit housing to cover the wires and make the design more appealing from a customer's perspective. This change would also help prevent bacteria from collecting into open spaces from the previous design.
These are the customer needs that needed to be met for this design. Some requirements that exceeded expectations were the cost, the overall dimensions and compactness of the design, and its lightweight.
So to make sure that our prototype met the customer needs and the design parameters, We underwent volume testing. So we bought a NEMA 17 single start stepper motor, which moves 1.8 degrees per step and has a pitch of 2 millimeters. So solving for the linear distance moved per step, we get a distance of 0.01 millimeters. Plugging that into the volume equation with our inner diameter of the cylinder being 6 millimeters, so the radius is 3. And then we get our volume per step of 0.2827 microliters. We divided our volume range from 10 to 200 microliters into 9 different increments and divided the volume by the volume per step to get the number of steps, rounding to the nearest whole number. And we went and did 5 trials per volume. On the bottom, you can see the chart shows each of the 5 trials as well as the averaged value and the average error for each of those volumes. On the right-hand side, we have a graph. We went ahead and plotted all of those points, the average points with the average volume, and then we fit a trend line in along with a tear value, which we'll use for the second round of testing. So for test 2, we're using based on the results of test 1 that we got. So we went ahead and added the tear value, and we calculated the new number of steps based on that new volume per step that we got. And for the second and third round of testing, we did three trials instead of 5, just to save some time because it was very difficult to find a time slot to use the test bench because so many groups were using it. And we also found that the range of values, they weren't ranging that much. So we found that 3 trials was enough for the testing. We went ahead and did the same thing. The bottom chart shows the average and the error, and the graph on the right shows the new volume per step. And for the second testing, we went ahead and set the intercept to 0 because we figured at 0 volume, there will be 0 error since it's not sucking anything up. So for the third testing, there was no tear value. This was our final round of volume testing, and we found that pretty much the volume per step was adequate, solving for doing the same process that we did in the first 2. We went ahead and did 3 trials, and the average error showed that we were within the customer needs of 1 microliter when we factored in the error of the scale.
So the Reynolds number was of interest to be calculated because one of the customer needs was to avoid creating aerosols. So we figured laminar flow would not allow for creation of aerosols. So from testing, we saw our system could pick up and dispense 350 microliters per second. And the diameter at the very end of the pipette tip was 0.61 millimeters. And the dynamic viscosity was taken at the lowest temperature of the customer requirements, which was 4 degrees Celsius. That's shown on screen as mu. Solving for the velocity at the tip of the pipette, we get 1.2 meters per second. And plugging that into the Reynolds number formula, we get 465.9, which is way less than the 2300 to be considered turbulent flow. We did in fact have laminar flow.
In order to meet the customer need for ejecting the disposable pipette tips, the tip ejection force is calculated. The friction force caused by the press fit has to be overcome by the maximum motor force. In order to solve for this, we must calculate the pressure caused by the press fit between the pipette tip and the shaft it attaches to. Using the interferences deflection, the shaft diameter or subscript S, the pipette or hole inner diameter or subscript H, and the elastic modulus and Poisson ratio for both the shaft and pipette tip, we calculate that the pressure of the press fit is 0.355 newtons per millimeter squared, or 0.355 megapascals. By multiplying that pressure value by the area of engagement and its coefficient of friction, the force needed to disengage the press fit is calculated being around 10 newtons. The maximum force the NEMA 17 motor can produce is 224 newtons, which is well over the amount needed to overcome those 10 newtons of friction force. Therefore, the pipette tips will be ejected without issue.
A snap fit analysis was conducted in order to determine the proper dimensioning to prevent failure. The maximum allowable deflection needed to be under 0.42 millimeters. The deflection of our snap fit is 0.25 millimeters, which comes in under the maximum deflection. The perpendicular force was found in order to determine the mating force. As shown, the mating force is 5.7 newtons, which is a little over 1 pound of force.
So the entire cost of our pipette design ended up being a little less than $72, with most of that being the off-the-shelf parts, the motor, the lead screw nut, all the fasteners, and the tool plate parts being the connectors, the magnet, ball bearings. The 3D printed parts only cost a little over $7. That price was found. You put your STL CAD model into Prusa Slicer, and it would output how much material would use and how much cost based on that material. The raw materials are the aluminum bar stock bought from McMaster, used to machine the pipette cylinder and plunger. The machining cost was a little over $2, and the assembly cost was a little over $3. And that comes from all 6 of us started with the entire pipette completely disassembled. And we timed how long it took to fully assemble it, and we averaged it divided by 6. And that came to be 12.45 minutes at 16.21 an hour. That comes out to be $3.37. Prusa Slicer also tells you how long it takes to print. It's a pretty long print, being a day, 4 hours and 14 minutes, and it uses 209,000 millimeters cubed of PETG filament.
So why should we be selected? Our pipetter has a slim, sleek, and streamlined design that stands out from existing pipetters on the market. It dispenses liquid at a high accuracy of 1 microliter. It is lightweight, weighing in at 0.587 kilograms. It has minimal parts, which would include the tool plate and hardware, and this would allow for ease of assembly and disassembly. And the prototype itself is at a low cost, totaling to $71.70. Thank you for your time. We'll now open it up for any questions.
Okay, great. Thanks for your presentation. Let's open the floor to questions from our panel.
Hi guys, this is Elise from Cummins. Yeah, good job on the presentation. I liked how you had that section view at the beginning, and you showed your customer requirements, and it was nice to see the press fit calculations and that 3D printing cost time. I don't think I've seen anyone do that. Can you go back to your cross-section view? Okay, so what is the was it the ejection mechanism? Is that 3D printed there?
Yes. All parts are 3D printed except for the piston, the pressurized, that was made out of aluminum. So just the plunger and then the hollow cylinder were both made of aluminum. That was the 3D printed part was tapped and then screwed in was the aluminum parts to create the piston.
Are you concerned at all about the 3D printed threads wearing out or maybe over time at all, or their accuracy?
So when we printed the parts, we printed a hole and then we tapped them so that it wasn't reliant on the 3D printer to print the threads. So the initial insertion of the aluminum in the plastic would be the only time that it would create that. Over time wear, it might, but the pressure is extremely low versus the plastic wear.
Okay, thanks. So where do you think this mechanism could fail? This where do you see this most likely to fail? Did you do any analysis on that? Like on the 3D printed part?
We were thinking the O-ring losing lubrication over time and maybe wearing, but we didn't do any kind of fatigue life testing or wear testing of the O-ring. But that's where we think it would fail if it wasn't properly lubricated.
Yeah, as well as the let me go to the customer needs slide. Our motor has a 10,000 hour motor life, but the operational lifetime calls for 10 years. So it's really dependent on how often the motor is going to be running. We calculated 10 years to be a little bit over 87,000 hours. So on average, it wouldn't be able to run more than 2.74 hours per day. And we expect the testing to involve, like some days involve like 10, 12 hours, and then we assume that some days it won't be used at all. But it really depends on how often they're going to be testing, as well as the temperature, the internal temperature, depending if it's running at 4 or 70 degrees Celsius.
Oh yeah, I don't think anyone's really talked about the temperature range at all that the printer is going to be operating at. So that's a good point there. I guess you could look at the 3D printed material, how its strength varies with the temperature as well. But yeah, thank you.
Thank you.
So this is Rick Miles at Northrop Grumman. Good presentation. I really liked the look of your final design, right? It's very aesthetically pleasing, but I do have some concerns with the fact that you're 3D printing so many parts. If you go to mass production, right, then I think you're going to have some problems with producing some of those parts, say from an injection molding type approach. The other thing is on a lot of your slides, you provide way too many long numbers, too many significant figures, right? You need to keep those things fairly neat and tight on some of those numbers. Like you mentioned cubic millimeters, but it's a very large number. So you might want to present that volume in a different manner. But yeah, my biggest concern is just with how many parts you're actually going about and 3D printing. I think that's going to cause you problems down the road.
So there are 5 3D printed parts. It's just 2 are quite big, but definitely in mass production, you'd make a mold and do injection molding.
And I can chime in a little bit on the 3D printing. That was actually one of the directives we gave them at the beginning of the semester to keep them making iterations as quickly as possible, was to 3D print parts that sometimes might be otherwise even machined parts, at least at first, just that way we didn't overload our manufacturing capabilities.
Okay. That's good clarity. On another thing, you talked about the assembly time being almost 13 minutes. And I guess I'm looking at your particular device here. I'm having a tough time seeing where all that time is coming from. What's driving that assembly time?
A lot of it comes from soldering. We each soldered 6 wires because it's you need 4 for the motor, 2 for the limit switch, and really none of us are great at soldering. We haven't had much practice. I know that was my first time soldering, so definitely took a long time to get it right. A lot of messing up, but that was all factored into the time.
Okay,
Also-
good. That provides some clarity. Thanks.
Yeah, and we have quite a few fasteners. We have 2 for the limit switch, 4 for the motor. So that adds time as well and also 3 for the tool key, which also have nuts on the other side of the bolt. So it takes a little time for that.
So yeah, so on that, right? So one of your requirements from the customer is a toolless type, but I think you ended up having to use screwdriver and Allen wrench. Is that basically where you're limited?
Yes.
Okay.
That's ultimately why the housing ended up being snap fit, just to clean up the whole design and kind of encapsulate everything.
Okay.
Okay. We've got, oh, here comes Tom from Northrop Grumman. Be afraid. We've got about 4 minutes left in this session. So if there are other questions from our panelists. No. Okay. Well, seeing no questions, we'll wrap it up just a minute or two early. Actually, this is nice. It gives everybody just a chance to take a breath before we jump into the next one. So I just want to reiterate my thanks to this group for all the hard work you guys put in this semester and sharing your design with us. We appreciate your time. Well, gosh, it started out as this morning and now it's this afternoon. So we appreciate your time both this morning and this afternoon in sharing all this work with us. So very good job. Well done. And as Dr. Nemi would say, you guys are free in air quotes.
Thank you.
Thank you.
Thank you.
Thank you.
Very good. Okay, well, let me stop recording.